What is up, everybody? Today we're going to talk about Ethereum rollups. So, as you guys probably all know, the mainnet on Ethereum is really slow. You can only process around like 20 transactions per second, and if Ethereum is going to become its vision, or if Ethereum is going to become like having hosting a lot of applications in the future, then you really got to increase the transaction speed and make it so that it's compatible to do all these sort of big things that it's like designed to do. And this slow transaction problem is called a scalability problem. So this scalability problem has been here for Ethereum for since the beginning of its creation, in fact, and scalability is one of the things that Ethereum needs to fix, and it's actually probably now the only thing that Ethereum needs to fix now that Ethereum has launched into proof of stake right now, and it's pretty decentralized and it's obviously really secure. And the thing that it needs to work on is obviously its scalability. You can't work with 20 transactions per second if you're going to make these big dApps. So right now it's 2023 and there has been some efforts in order to boost the scalability for Ethereum. And if you have looked at some other chains as well, for example, like Solana, uh, Cardano, Algorand, they have much higher scalability than Ethereum. They can process much more transactions than Ethereum. But the things some of these chains that I mentioned just now are lacking are the decentralization and the security, which Ethereum has. And the only thing right now that Ethereum needs to fix is its scalability. But how are you even supposed to fix it? So actually, there are two methods that we can take to increase the scalability for Ethereum. The first method is to increase the mainnet's transaction capacity. What this means is that basically Ethereum is like is a chain. So the first increasing the mainnet's transaction capacity means improving the chain so then the chain can be able to process more transactions on the base layer. So essentially when you increase the transaction capacity, obviously you can perform more transactions and it will become more scalable. This is one option, but it could be a little bit hard to process this and execute this. The second option that we're going to look at in this video is to move some of the computation off the mainnet. So essentially on the chain, obviously there's a lot of computation going on. You got to do a lot of computation, a lot of transactions, all that stuff, a lot of data on the chain, and all these can actually decrease the scalability. My bad. All these can decrease the scalability of the entire network because in order to like run a node on there, you need to like store all this data, store all this chain, all that stuff, and which will actually decrease its scalability. So if you do these two methods, then you can actually increase the scalability of Ethereum. And the second method is the one we're going to talk about. And when we move the computation off the mainnet, which I just explained, where are we going to put it? Where are we going to put and process all of these computation? So we're going to put it on something which is called a layer 2. Instead of putting all the data and the computation on the blockchain directly, you can put and perform most of the data and the computation off-chain. Hence, this is called a layer 2. So essentially what this is like you have the base layer, which is Ethereum, which everyone is talking about right now. It's like the place where all the transactions are happening, all the contracts are executing, all that stuff. So this can be like the base layer. And then off-chain layer 2 is just like a separate layer which is connected to the base layer, which is the layer 1, and it's just like a second layer to like the main layer. So for example, like it's like a hamburger, I guess. Like the thing which you see in the hamburger is obviously like the bread on top. So the bread in this case is gonna be the Ethereum layer 1. But then if you're just eating bread yourself itself, then it's not really that tasty, right? You need like all the ingredients underneath the bread. So all those ingredients underneath the bread is the layer 2. And in this case, the layer 2 is going to power the layer 1 to increase the scalability of the layer 1. Just like how like if you put the ingredients in the hamburger inside, the hamburger will obviously be more tasty and you eat it. So there are three types of these kind of layer 2s. The first type is a plasma layer 2. second one is the state channel layer 2, and the third type is a rollup layer 2. So I won't go into Plasma and the state channels in this video, but then I'll talk about rollups layer 2 because all of these different types of layer 2s have some similarities and differences. But the thing about rollups is that, first of all, the rollup industry on Ethereum is booming right now. Literally, you have all these new uh, different rollup solutions such as CK Sync. This is Starknet, this is Optimism and Arbitrum, which we'll go into a little bit later. And rollups has really been like a topic that everyone has been discussing for the past year or so. And now even Vitalik Buterin highlight that he's actually really excited for more development on rollups this year in 2023, and it's just exponentially bullish on rollups as well. So this is something good to understand, and we're going to cover rollups in this video. So what does a rollup exactly do? Based on our previous definition from this slide, we are going to move the computation, which is also like the storage, off the chain, and we're going to keep some of the data per each transaction on the chain. So what does this entirely mean? It means like you're going to put all like the computation and storage, which is like originally processed on the layer 1 or the mainnet, depending on what you call it, and then you're moving it to this layer 2, aka the rollup. And you're going to keep some of the data per each transaction on the chain. So data per transaction could include like wallet address, gas, amount of gas you paid, amount transferred, the message being sent, just basically all like the data involved with like each transaction. And you're gonna keep some of that on the chain. So probably it's easier to track all the transactions while you move all the computation and storage off chain. So essentially this is what a rollup wants to do. So rollups function in this way. But what's the benefit of a rollup then? The first benefit that I kind of mentioned just now is that anyone can locally process all of the operations in the rollup if they wish to. So, for example, you can even withdraw funds, process transactions inside the rollup, and you can also detect like vulnerabilities and fraud inside the rollup. So essentially, like whatever you can do on the mainnet, you can sort of do on the rollup as well. And that's not really the case with other two examples that I mentioned just now, the Plasma and Stake channels, because it's actually limited in some applications that we won't talk about in this video. But rollups is like more general purpose, and as I said, anyone can locally process all the operations inside the rollup. And second of all, based on our previous slide, since some of the data, which is the data per transaction, is still kept on chain, bad actors, essentially just like hackers, they can do very little harm to the rollup, which will also help with verifying transactions easier. If all of like your data is on the it's all of your data on the rollup is all about computation, but the data per like each transaction, which is one of the most important things for Ethereum to process transactions, this data is still kept on chain. The hackers can't really do much bad things inside the rollup, and essentially that will also help with the entire transaction verifying process. The third point, which is probably the most important point, and probably the most important point why everyone in the Ethereum community is really excited about rollups, is because you can literally run the Ethereum virtual machine inside a rollup. So if you don't know what Ethereum virtual machine is, I'll go over that in another video. But essentially what this allows you to do is that it allows you to literally run existing Ethereum applications inside rollups. So for example, one Ethereum application is Uniswap. So you can literally like easily migrate to a rollup, and it will be really easy to do because like you can literally run EVM inside the rollup. And because of this, we can potentially see many existing Ethereum applications in the future migrate to different rollups, and as a result, there will be more activity on rollups, and this is essentially why people are really into rollups, and probably one of the next big things in Ethereum, which will help with scalability, a problem which it has been facing a long time. So again, just to recap, rollups are the most general purpose kind of layer 2s. But how does it all work? if you want to know how it all works, let me tell you how it works. So essentially, on the mainnet, you have a smart contract. I'm assuming you know what a smart contract is. Let's just call it the rollup contract, and it's on the mainnet. And then in this smart contract, it will store a variable called the state root. So what is the state root? Essentially, the state root is just it's like the information of the rollup. As you can see, this is the smart contract on the mainnet, and this state root is correspond to 0x6969420. And as you can see over here, this is the exact same number, and over here you have all these like information about like the balances of like different nodes on the mainnet. I mean on the rollup. So essentially, to recap, a smart contract on the mainnet keeps track of everything which goes on the rollup. That's why I nicknamed it the rollup contract. And this state root corresponds to Merkle tree. So essentially, what a Merkle tree is that it's data structure that's used to like verify the integrity of data inside any like computer system, and it basically does this by creating like a tree-like structure with different hashes, which are like digital fingerprints of the data at each level. So essentially, it's just basically like a summary and like information of like the entire everything which goes on the mainnet. I mean on the rollup, and everything which goes on the rollup, you can label it with this number, and this number is a state root. So this is the entire diagram to show how the rollup is connected to the smart contract. And then let's say that you perform like a transaction on the rollup. Then this will get displayed on the mainnet, and basically each transaction on the rollup is called a batch. So assuming this batch is batch number 420, and then in this batch you have information such as Callum gave Ruxin 80 x66 tokens, and Jamin gave Seb 40 x66 tokens. So essentially these are just transactions, and the batch stores information about these transactions. Inside this batch, apart from the actual transaction and the actual message, it also has to like display the previous state root. So the previous Merkle tree of the entire rollup. And as you can see, this previous state root is the exact same state root as the one on the smart contract. The smart contract which basically summarizes the entire rollup. And then after that, you also have to provide something called new state root. So let's just call this the post state root. And then basically what this does is that the state root changes from the original previous state root to a different state root. And because essentially when we're like doing a transaction, we obviously have to change the Merkle tree, the data structure, which is summarizing the entire rollup. And since we're changing the data structure, since we're changing the Merkle tree, we also have to change the state root as well. So as you can see, the state root has changed from 0x6969420 to 0x1234567. And this will be the resulting state root of the Merkle tree. And then once we have this is basically like the old rollup Merkle tree. And then this batch is being updated to the mainnet. It provides the information of the transaction, what we saw before, the previous state root and the post state root. And then once this transaction is verified, this previous state root will change for this post state root will change for the rollup, and the state root changes to the post state root. So as you can see, once this batch is submitted, once this transaction is submitted, this state root, the previous state root will change to this new state root. And also, the values are updated for the Merkle tree. That's why there's a change in the state roots. And also, the most important thing is the smart contract, which keeps track of the entire rollup. Its state root has changed, so it's corresponding to the most updated version of the rollup. You can put it that way. But hold up, there's a problem. How can we like verify that the post state roots presented in these batches are correct? Like someone could just literally submit a batch with any like sussy post state root with no consequences. They can just transfer all the coins inside the rollup to themselves, right? Like you can just literally post something on the rollup, and then this basically without any verification, you can just literally do something which takes all the coins and takes all the tokens and gives it to yourself. And therefore you're just changing the post-state root. But then how can we verify that this new post-state root which is presented in the batches are correct? Or else if we don't verify it, then the Merkle tree is going to be changed and the smart contract is also going to be corresponding to this fraud rollup. This brings us to two ways that we can verify that the post-state root presented in the batches are correct. And this is the battle of rollups, which a lot of people has been talking about inside the rollup community. It is optimistic rollups versus zero knowledge rollups. I'm sure you have heard about this battle before between these different types of rollups. It's actually because you have two different ways to verify. So it provides you two different options of rollups and two different types of rollups. And you can group these two types into optimistic rollups and zero knowledge rollups. So Arbitrum and Optimism are optimistic rollups, and CK-Sync and StarkNet are zero knowledge rollups. So people have been debating which type of rollup will eventually win out this entire rollup battle. I won't really get into like the major details about the optimistic rollups and the CK rollups as much as I cover like the Merkle trees, the state root, how all the rollups actually work. I'll just briefly talk about the major differences between these two types of rollups. But as you can see so far, as of January 3, 2023, optimistic rollups are currently winning the rollup battles in terms of total value locked. But this might change with the introduction of zero knowledge rollups, as in Web3 the industry moves really quickly. So you have Arbitrum, Optimism, all of these optimistic rollups on top, where in terms of total value locked, so which means that more usage on these protocols, these rollups, and you have these like zero knowledge rollups at the bottom. But who knows, it might change in the future. And this is part of the battle as well. And as you can see, the major usage of rollups has actually increased much more over these recent months, years, as the absolute monthly gas use has increased in this period of time, which means there's more activity on these rollups. And this corresponds to the battle of the rollups and the increasing hype and attention to Ethereum rollups. So let me just briefly talk about optimistic rollups. So the way that optimistic rollups verify that the post-state roots presented in the batches are correct are by using something called fraud proofs. So essentially the rollup contract keeps track of the entire history of the state roots, as we all saw, and the rollup contract will keep track of the hash of each batch submitted. So every single time you submit these kind of batches, it will just basically hash it and it will provide you a hash. Just basically like a label for the batch. And basically, since you have like the entire history of these hashes and you have the entire history of the state roots, if someone discovers that the post-state root presented in one of the batches is incorrect, like for example, you have all these history available public, and if one of these post-state roots presented is incorrect, they can publish something called fraud proof. So the fraud proof is essentially includes just the evidence that what someone claims in step one is true. And then if that's true, it will prove that the batch was computed incorrectly to the chain. And then the contract will verify the proof and it will revert the batch and all batches after it. So essentially this is how optimistic rollups work. It's just like, for example, like I don't know, like you have a bunch of like cars, and then uh basically each car has like a different license plate, and then someone says that that's their car, but then they provide like a fake license plate, and then someone goes through the history of like entire cars, and then they say, hey, that's not true, and then they list out the evidence and stuff, so that if what the accuser says is not true, then basically this is what can happen. The contract provides proof and reverses that the batch and all batches after it. So this is how optimistic rules work. What's the zero knowledge rules? How they work? It's really interesting, as it involves a lot of cryptography and advanced cryptography, basically, to understand the validity proofs. So Optimistic rollups use fraud proofs, zero knowledge rollups use validity proofs, and as I said, they use cryptography to verify and prove that the post-date root percentage batch is correct. So they use a lot of complex advanced math and scientific method in order to prove that the post-date root percent in the batch is correct. The good thing about zero knowledge rollups is that no matter how large the computation is for proof using these validity proofs, the proofs can be verified very quickly on chain. And then here's just like a breakdown between optimistic rollups and CK rollups, which contributes to like the battle between them. So as you can see, the fixed gas cost per batch, optimistic rollups really win out in terms of the fixed gas cost per batch, as requires less gas because you're just changing like the state root of the like the fraud piece of old state root. But then for the zero knowledge rollups, obviously you need more gas as the cryptographic verification is really quite computationally intensive. Obviously you take longer time to withdraw funds for optimistic rollups. You need like around 1 week to withdraw funds, because like you need to literally wait until someone publishes a fraud proof, and if the fraud proof is true, then you need to cancel the withdrawal if it's fraudulent. So it'll take 1 week. And for zero knowledge rollups, it's just gonna be really fast because for each batch, no matter how large the computation, it can be quickly verified. And the complexity technology optimistic rollups is low. It's just basically like you find this, then you prove it. And obviously for zero knowledge rollups, the technology is pretty complex because it involves like advanced cryptography. The generalizability, I have no idea why I can't pronounce this word. Essentially, the optimistic rollups, it's obviously easier to develop them and easier to generalize applications of them. And obviously for zero knowledge rollups, it's harder in terms of compared to optimistic rollups, as it's a new and complex technology. For the per transaction on-chain gas costs, obviously the zero knowledge rollups is going to be lower, and the optimistic rollups is going to be higher, because essentially you're just going to process all the zero knowledge validity proofs on the chain, and it's going to be pretty low, but then each transaction is going to be submitted really quickly. And the off-chain computation cost for optimistic rollups will be lower, though there's actually you need more full nodes to redo the computation for the fraud proofs on the rollup. Alright, thank you for watching a video about rollups. Basically in this video, you guys learned about what are rollups, why is it so important in terms of scalability, how do rollups work, and the two different types of rollups, the optimistic and zero knowledge rollups, and the differences between them. So I hope you guys enjoyed this video. Don't forget to subscribe and like our channel. Check out our website for more information about events that we're hosting in the future. And I wish you a good day.